The textbook includes this equation for volume in decibels. It's kind of a complicated looking equation, but to me it's an excuse to talk about log tables and slide rules. Volume in decibels, beta, is equal to 10 decibels times the log base 10 of the intensity divided by I naught. A baseline intensity I naught is equal to 10 to the negative 12. Well, that's really small. 10 to the negative 12 watts per meter squared. That's energy per time per area. And what does that mean? Well, one thing that means is that 0 decibels does not mean 0 energy or 0 intensity. It also means that increasing the decibel level by 20 means you have 100 times the energy. Increasing the decibel level by 40 means 10,000 times the energy intensity. Increasing the decibel level by 20, that's right, increases the energy intensity by 100 times. Increasing the decibel level by 10 is 10 times the intensity, the energy per second per area. And increasing the decibel level by 100 decibels means what's that? 10 billion times the intensity. So log scales are pretty cool because they do stuff like that, but what I'm interested in is how exponents, and if you followed through that explanation that I gave real quick there, you already know that exponents turn multiplication into addition. 10 squared times 10 cubed is equal to 10 to the fifth. You're still with me, right? And that's good because we're going to use this fact that exponents turn multiplication into addition as the power source that makes the slide rule work. But who's talking about exponents? We're talking about logarithms. Well, logarithms undo exponents. And if all you know about exponents is that it's kind of like successive multiplication, there's a lot more to know. After all, what does it mean to multiply 10 by itself 2.5 times? We'll get to that later. First, before we get to the log table and the log book, not that kind of log book, and the slide rule, we'll start with the calculator, which is a really recent invention in the grand scheme of things, and the log button on your calculator. Find the log button, and if you have the time, please convince yourself that the log of 0.01 is equal to -2, and the log of 1,000 is equal to 3, and then convince yourself that it is true. Log x equals y if 10 to the y is equal to x. That's true. 10 to the -2 is equal to 0.01. 10 to the third is 1,000. Notice the log button on your calculator assumes base 10. You can do logarithms in other bases as well. Our challenge will be to take the logarithm of 2,180,000 and the logarithm of 1,550,000,000 because I'd like to multiply those two numbers together. Your calculator could do it, but we're going to do it with a log table, and then we're going to multiply those numbers together. Gross. How can you multiply those numbers together? Well, one thing you could do is you could put them in scientific notation. 2.18 times 10 to the 6th. 1, 2, 3, 4, 5, 6. Yeah, that works. 1.55 times 10 to the 9th. That works too. And in a way, logarithms and scientific notation, they're kind of related. They're like second cousins. But even with scientific notation, this would still be an arduous mathematical multiplication. You'd have to do 3 digits times 3 digits, be my guest, but I want to use logarithms to do that, to find that 2,180,000 really is equal to 10 to the 6.34. Again, how do you multiply 10 times itself 6.34 times? And how did I find that number? With a log table. First, we recognize the 6. See, I said they were cousins. They're cousins. The 6 tells us about how big. But where did the 0.34 come from? The 0.34 came from this table. All right, see, we have 2.1. All right, that's in this row, and 2.18. That's in that column, and there's our value, 0.338. And you'll excuse me as I round that to 0.34. Congratulations, we used the log table to evaluate 2,180,000 equals 10 to the 6.34. Now let's do it with the other number again. I know where the 9 comes from. But it's the 0.19 that I'm interested in finding. 1.5, that's across that row there, all right, 1.55. 1.55, and that's where my 0.19 came from, 0.190, so no rounding here, thankfully. Great, we've expressed these two very large numbers as powers of 10, and now we can multiply them together because, like I said, exponents turn multiplication into addition, and I can add 6.34 plus 9.19, adding three-digit numbers easier than multiplying together two three-digit numbers. That's 15.53. And now the question is, how can we get that? That's power of 10. How can we get that out of a power of 10? And the answer is, again, the logarithm table. Let's find 0.53. Scanning around. There it is. Again, we're not too concerned about the 15 right now, but 0.53 corresponds to 3.39. 3.39. So there we have it. 10 to the 6.34 times 10 to the 9.19 is equal to 10 to the 15.53, and that equals 3.39 times 10 to the 15th. You just multiplied two huge numbers using log tables. Congratulations. Check your work with the calculator. I'll wait, and you'll see it's not exactly correct. Oh, no, it's not exactly correct. Your calculator gives you a value that's a little bit different. And I'm not going to tell you what that other value is because I really want you to check this. What could the problem be? Where did I make Oh, I rounded. There was a little bit of rounding, and that's why that third digit, that third significant digit, is a little bit wonky. It should be closer to something else, that third significant digit. Turns out, though, fun fact, if we were to use this log table that I was using, and even without the rounding, we still would not get the exact answer that your calculator is giving you. You would, however, if you use the 5-digit, not a 3-digit log table, but a 5-digit log table, and that's why people invested in those books. Not just because they look pretty handsome on a bookshelf. Anyway, close enough for me. I think that works, and let's now use those facts with the slide rule because I want to get my hands on a slide rule. First, the slide rule has strange scales on it. They have logarithm scales, and since we're experts at logarithms, you can convince yourself that log 6 is 0.78, or 10 to the 1.47 is equal to 30, or log of 400 is 2.60 because 10 to the 2.6 is 400, and we can graph those facts on two different scales. Here we have the 0.78, the 1.47, and the 2.60 graphed on a traditional scale. We also have the 6, the 30, and the 400 graphed on a log scale. Changing the scale changed whether or not that dot represented a 6 or a 0.78. On the top scale, notice that the difference between 0 to 1 is the same as the distance between 2 to 3. On the bottom scale, the distance from 1 to 10 is the same as the distance from 100 to 1,000. Also, the log scale, notice, does not start at 0, starts at 1. That's why 0 decibels does not mean 0 sound energy. Our next step is to use this fact to turn multiplication into addition with logarithms. If exponents do that, logarithms do that backwards, sideways, or in a mirror or something. Log 6 is equal to log 2 plus log 3. That's right. 6 is equal to 2 times 3. There's log 6, there's log 2, and there's log 3. And we know that this in red is equal to that in green plus that in blue. We know that. We can add those together. Life is good. On the log scale, it's true that 6 is equal to 2 plus 3. In this presentation, we are studying the fact that 6 is equal to 2 plus 3. No, it's not equal to 5. I mean, it would be if we weren't talking about logarithms, but the log of 6 is equal to the log of 2 plus the log of 3, turning multiplication into addition, and that is exactly what your slide rule does. Here we have 3 times 2 is equal to 6. The 3 on that scale, the 2 on that scale, and the 6 on the scale on the bottom. Again, 3 times 2 is equal to 6, shown with the slide rule, shown with log scales. Hooray, we're done, or almost done. And of course, if you can do multiplication, then you can turn this thing backwards and do division. But here's another question. How can we multiply 3 times 6? So of course, 3 times 6 is equal to 18, but you can't really show that on the, you can try, but it will go off the scale. See what we're doing here? We're having 3 times 6 goes off the bottom scale. So how can we figure out? Well, they don't call it a slide rule for nothing. We'll slide it backwards. and further backwards until we put the 10 at the 3, and notice the 1.8. Look at that, it's between 1 and 2 on the log scale. It's a tricky log scale there, but there is your 1.8. Like we said earlier, you kind of have to figure out the power of 10s on your own, but there it is, 1.8, but you know it's 18. And why does that work? Well, we agree that log 3 plus log 6 is equal to log 18. Addition turned into multiplication through logarithms. That's what we're talking about. Put that up there and then subtract log 10 from both sides of the equation. So far, so good. Rearrange. All right, distributive property, a negative turns into a positive. I like this so far, and that's exactly what we said with the wraparound method. That is what we said with the wraparound method. If you don't believe me, consider this red box. Consider this purple box. Consider this blue box. The purple minus the blue together is the yellow. See the purple, the log 10 minus the log 6, that is the difference between log 6 and log 10. So that's the yellow. And then the red minus the yellow is the green. And this green is equal to that green. And you can now take your slide rule and multiply the world.